interested in an initial value problem where the initial condition is discontinuous, a jump between, say, UL for left and UR for right. And I was going to illustrate a couple of these solutions with the lax shock and the rarefaction wave. So first of all, let me talk about the characteristics. So if I have a characteristic x equals ut, for instance, and u is constant on that characteristic, and I've drawn it through the origin, so the x0 is 0. And in a lax shock, the characteristics on which u is constant converge on the shock. So over on the left here, I have x less than st, or x less, let's call this speed s. And over here I have x greater than st, u is u right. Oops. Here u is u left. And if I look at the graph of u, and I have ul is bigger than ur, here are the two values of ul and ur. And the shock moves with a particular speed, which is just the average of the left and right constants. It's an explicit weak solution of this nonlinear partial differential equation. And it has this property, this admissibility property, that characteristics converge on the shock. On the other hand, if ul is less than ur, I'm going to do this like this. So here's ur, here's ul. Then you have a shock, you have a rarefaction wave. So here u is x over t, and at type u, the piece of the solution is moving with speed x over t. So this is a widening wave, but it's continuous. It's a rarefaction wave. U is rarefying, like a rarefied gas. Whereas a shock could be a pressure wave in a shock wave in the gas. Okay, so that's the Invisib-Burger's equation briefly. You're probably familiar with Burger's equation, the second equation here, where it's really a nonlinear heat equation. In fact, the Kohl-Hopf transform converts it into a heat equation, and that gives you the method of solution by solving the heat equation, especially for the Cauchy problem. And then finally, a dispersive equation, which I'm going to talk about, is the KdV equation, or Korteweg-de Vries equation, famous prototype of nonlinear dispersive equations. And famously, we have solitary wave solutions. So the dispersive term is this third x derivative. Nu, again, is a parameter that can be positive or negative. But instead of having a shock wave, as we would for the Invisib-Burger's equation, for the KdV equation, we get something called a dispersive shock wave, which I will show you. It's a spreading wave with lots of oscillations. The dispersion is the oscillations. But in the rarefaction wave case, we still get a rarefaction wave, but with small oscillation. Okay, so that's sort of a very brief introduction to the sort of nonlinear equation I'm going to be talking about. However, for Burger's equation, now my change is not working again.
No.
Yes, good. Yes, thank you. So at the top here, I have the BBM equation, or so here are the names, Benjamin, Boner, and Marnie, BBM equation from 1972. And it looks a little like the KdV equation. There's an additional linear transport term, the CUX term. But the dispersive term, instead of having 3x derivatives, has xxt, so 2x and the t derivative. And in fact, in the long wave limit, it's equivalent in the asymptotics to the KdV equation. So it was proposed by Peregrine in '66 as an undular bore, like the 7 bore. And in '67, it was introduced as a model. for waves on a beach. And then in 72, it was analyzed by Benjamin and co-authored workers. The Riemann problem, as I had earlier, I've now switched notation slightly. UL has become U minus and so on. But we're actually going to smooth the initial condition with a width C. So that's this hyperbolic tangent function. So it asymptotes to U minus as x goes to minus infinity and to U plus as x goes to plus infinity. But it's smooth and it's a sharper transition as C gets smaller. Okay. All right, so I'm going to talk about some basic properties, and I'll tell you what the solutions of this Riemann problem with jump initial condition looks like, and then that'll throw up lots of questions as to where do we get these solutions from. All right, so basic properties, this BBM equation. What's this one? Okay. First of all, I can write a simpler version without that linear transport term by moving in a moving frame, going to a moving frame. But I can also shift in U. I said this is a Galilean transformation, and if I start with the equation 4 here, I then get back to that equation with a linear transport term. There's what's called a dispersion relation. This is the linear for the linearized equation. So I linearize about the background UB is the linearized equation, and look for exponential solutions. So there's a wave number k and a temporal frequency omega. So that's the frequency of oscillations in time. And the wave speed here would be omega over k. All right, so if I substitute in this exponential, then I find I can solve for omega, and I get a bounded relationship between omega and k. Whereas for the KdV equation, that relationship is unbounded. That's a key ingredient, a key difference between the equations. I can differentiate once to get the group velocity, and a second time to get something that's called the dispersion sign. And you'll notice that these quantities are 0 at special values of k. K equals 1, k equals 0, and k equals square root of 3. And again, that will show up a little later. Now, back to the Riemann problem, we have a phase diagram which takes a little bit of explanation. So first of all, on the left, I have U minus against U plus. So this is supposed to indicate the solution for every choice of constant U minus and U plus. Remember, for the invisib-Burgers equation, no dispersion, there are only two solutions, a shock solution and a rarefaction solution. And the remnants of those solutions are shown here. There's a rarefaction in here and over here, and the shock gets replaced by this complicated dispersive structure. That's a dispersive shock wave. But there are other solutions as well. So first of all, this upper part of the plane with U plus bigger than U minus U minus, U plus plus U minus positive, is shown up in this up here, where I've labeled the various sectors because the solutions change as you move between sectors. So on the diagonal, with U plus positive, we have a solution that looks like this. It looks like a rarefaction wave that's interrupted by a stationary shock wave that doesn't move. But in that shock wave, the left limit is less than the right limit. And that's, if you like, why you see the rarefaction wave. In B, so moving off the diagonal, you get that same structure. There's a discontinuity and a portion of rarefaction wave, but there's also something else that's going on, and that's actually a solitary wave moving off to the left. If I go to C, I get the solitary wave, and I get what we'll term a linear wave, small oscillations with a complicated structure, and the rarefaction wave. At D, we get another transition where the solitary wave has disappeared. And then in E, we have what we call the dispersive shock wave, again, with the complicated leading edge moving to the left. There's something that there are two other figures I'm not going to talk about, three other figures I'm not going to talk about, because there are a lot of things to talk about already. The dispersive shock wave, well, I'm going to talk about them very briefly, let's put it that way. The dispersive shock wave collapses at its leading edge. It's called an implosion, and there's an analysis of that. And then you give way to something that's trains of solitary waves going in both directions. And then finally, on this diagonal, where you would expect to see a classical shock wave, indeed you do, but there are also associated small oscillations. Okay, so that's the entire panoply of solutions, because below this diagonal, you just reflect the solution. Okay. All right. So here's a summary of the overall goals. I'm going to talk about these expansion shocks. That was the jump up, where the lax shock would only jump down. The structure of the linear waves, the shedding of solitary waves, where we saw that actually just one solitary wave, but actually there are others. And then an asymptotic analysis of short time of evolution. And then there's a threshold, as I'll show you in more detailed pictures. Okay, so that's quite a lot to analyze. I should say that the pictures here are all simulated from numerical simulations using a pseudospectral method, basically Fourier analysis. This is what a dispersive shock wave looks like, and although we won't see one as part of the explanation, at this level of refinement, they usually have additional, for the BBM equations, they have this additional complicated linear structure instead of just a smooth decrease in amplitude. But the structure here is that there's a solitary wave that leads the way. It's propagating to the right. And in the middle is what we call a modulated periodic wave. So the amplitude is obviously changing smoothly. The frequency or wave number is also changing as a function of this horizontal variable, the spatial variable. And the average, in fact, it looks very symmetric, but in fact, the average is also changing on that slow spatial scale. It's interesting because you can determine the two speeds, the speed of the small amplitude or harmonic waves and the speed of the leading solitary wave in the way that they depend on each other, even though you don't need to compute the entire structure of the wave. But that's another story. That's something called L's method. Oh, I should have acknowledged my collaborators, but I'll do that a little later. Okay, so shocks and rarefactions, that's the one that we had before. I wonder where that's. All right. Yeah, so this is the picture of the stationary shock. This is an earlier paper with the same collaborators. So we look at an initial jump up that's actually symmetric about the origin. And what we see is a decaying shock that doesn't move, a stationary shock. It's an expansion shock because the characteristics are moving away from the shock. On the right, the characteristic speed is 1, namely the value of u, and on the left, it's -1. So the characteristics are moving away from the stationary shock. So it should be unstable according to hyperbolic theory. We can do the numerics and we can do asymptotics. So the blue curves here are the numerics and the red dots are asymptotics. I won't tell you the asymptotics because they're quite complicated, but there's an incredibly good fit even out to time 100. And I mean, nothing small here, right? We're on this scale of 1 in U. We're going out to 50, -50 in X and for long times. All right, now if we look at asymmetric initial conditions, so here the U plus is 0.5, so it's way up here. So it's a constant out. You have to sort of imagine it in this picture. But we choose U minus to be two values, either minus 0.1 or minus 0.2. At minus 0.2, what we see is the same rarefaction x over t, roughly x over t, but there's a solitary wave that propagates to the left. If I change the U minus to minus 0.1, it looks as though there's a second solitary wave that's developing. And indeed, we can, as we gradually increase U minus, we start to see lots of these solitary waves, a whole train of solitary waves that are generated. And the expansive shock is still there. So you can only see purple here, but that means that green, red, and purple are obscuring each other. If I increase U minus further to 0, I still have the shedding of the solitary waves. But at 0.1, I get a single solitary wave, this orange one, and then something else which we'll call a linear wave. And then finally at U minus 0.2, the solitary wave's gone, and we're just left with the linear wave. Okay, so it's this picture that I want to explain, and it'll take me a couple of hours, but I've got about 25, 35 minutes. Yeah, so if we change the width of that initial condition, then we get a slightly different picture. It's just scaled, basically. The original one is C equals 0.1, and then the solid lines are C equals 0.05, and that's kind of interesting, and we can understand that scaling, but I won't go into that detail. All right, so let's start with the linear waves. It's a much simpler equation than looking at the full nonlinear equation. So for this picture, there's no solitary wave. We just have a linear wave train to the right, and then something complicated to the left of x equals 0. Okay, so first of all, the dispersion relation Greek velocity at the top, to remind you of those. And the singular values for the dispersion sign, k equals 0 or k equals √3 or u minus equals 0 are significant. So here's a graph of that group velocity against k. And it goes to the limit 0.2 as k goes to 0, and it goes to 0 as k goes to infinity. The same shape, this VG curve, on its side is here, where I've got k on the y-axis, but now I'm plotting against the solution and plotting how k varies as I move through this linear wave. So what happens is that we're on this branch of the graph of k essentially against VG, the lower branch, and there's a single spatial frequency that varies. It's modulated through this wave. Here it is in the crosses. But then there are two values of k, and we see a two-phase solution. So there's a single-phase solution, II has a two-phase solution, and then there's something fancy going on ahead of the wave. So all of those things can be explained with suitable asymptotics, and that's what's coming. This is a repeat of a slightly different simulation where there's more detail around to the left of x equals 0. So here's the single phase modulated wave. The amplitude is changing very slowly. Here's the two-phase solution, and then in the front we have a different sort of function. So the challenge is to capture all three types of behavior. Right, there's the initial condition. I take the Fourier transform and get these terms. There's a jump in the background, so that's that Fourier transform, and then this is this first term with a hyperbolic sign is the effect of the smoothing of the jump. We will partition into a nonlinear rarefaction wave for small k, and for large k, we get these linear waves fine. So for large k, right? So for large K, this delta function goes away. Here's the Fourier transform. And so we can write the solution of the linear equation. These are small amplitude waves. So it's a good approximation to look at the linearized equation around nu minus. And here's the solution where the exponential term comes from the dispersion relation. And then there's the K x over t, which is the piece of the rarefaction wave. Okay, so the contributions of the integral as t goes to infinity, which is, we're looking at comparatively long time. So we'll look at t going to infinity. And this is the stationary phase analysis. They come from critical points of that function chi that I had on the previous slide. And so here is how the analysis works. So we evaluate the integral expanding the Fourier transform of the initial condition and chi of k around these critical points, kn. There is either 1 or 2, right? Remember, that was where the derivative of the group velocity is 0, those dispersion numbers. Okay, so here's the formula. It looks sort of horrible, but this is basically a Gaussian integrated. And so we can evaluate the equations. In region 1, it's just a single phase. In region 2, it's a two-phase solution. And in region 1, we get a simple expression for the wave number, for K1. And so we can write the solution in terms of using the stationary phase analysis. In region 2, we have two values of K, K1 and K2, and a similar solution for each of those two values. We can add those together. It's a linear equation. And that explains region 2. Region 3 is interesting in a different way. There are the two stationary points come together. They merge at K equals √3. And when we expand, we lose the quadratic term in the expansion. Remember, in that in this Gaussian, we used an expansion to find the quadratic term. So now we've lost the quadratic term, but we get the next order term is needed. And it turns out that we get an Airy function, and the Airy function explains the shape of that leading order. And then you have to fit all these things together and get a solution, which now again is in red, and it fits remarkably well on the detailed solution. This is a blow up of what we saw before with the three regions, 1, 2, and 3. And the Airy function is out over here. The numerical solution is in blue, and the calculation that I just rushed through is shown in red. So this was really amazing to see. Okay, so now let's talk about the solitary waves that appear when we increase U minus, when we decrease U minus from the linear regime. First of all, solitary waves were studied by Kalish and Goen a decade or so ago. And we can write down an explicit formula, much as you can for the KdV equation. And this is a lot of detail that we don't need to know about, but there's a stability result that they had. And for our purpose, we get this hyperbolic secant squared. And there's a formula, and there's a restriction on C in terms of the background and so on. Okay, so there are solitary waves that are stable. Okay, so now how do we get this solitary wave? Remember, we start with a jump. Let's see. So yeah, we've got U plus over here and U minus over here. And then somehow propagating into U minus, a solitary wave appears. But you know, if I smooth this jump, everything's between U minus and U plus. So where does this dip come from? So we look at the early time and do an expansion. So the, oh, I can't use this. The U0 of x is that smooth jump. And then there's a first order term t times U1. This is amazingly naive, but it works. So we substitute into the equation, we get a term from u0 on the right-hand side and a linear term on the left-hand side. And we have boundary conditions. U1 has to go to 0 at infinity. We can solve explicitly for U1. And the solution as C goes to 0. So now we're making that smooth transition steeper and steeper is the delta function. And so if I go back and, yeah, so here's another ODE. Yeah, so C goes to 0. I guess that's this, this term on the right that we're evaluating. And then we can solve the equation and get an exponentially decaying term that's negative. Okay, and here's the result of that. And it's not such a, it's a really crude approximation, but as time progresses, we see the initial jump, which is not really shown here, but you can imagine it, two horizontal lines. And on a rather small scale of x, you see the expansion shock and you see a dip developing. Again, there are the asymptotics and the numerical solutions together. I can't remember which is which now. Oh, solid and dashed, and at 3 different times. And then if I subtract off the initial condition, you can see how the dip is modifying U minus. So that's just taking away the expansion shock piece from near 0. Okay. So again, remarkably good agreement. And then we want to look at this tricky problem of why the solitary waves appear and then disappear. And I'm not going to talk about the train of solitary waves we saw. That's a rather more technical topic. And we haven't actually written about it yet. So that's, if you like, research in progress. So the problem is outlined at the top to find a sigma depending on this width, so that a solitary wave is generated if U plus is bigger than sigma times U minus, but no solitary wave for U plus less than sigma U minus. So typically we're going to fix U plus and vary U minus. Think of it that way. So we'll fix U, eventually we'll fix U plus equal to 1. So the threshold is determined by considering energy. So here's the energy distribution, U squared plus UX squared over 2. That's conserved for smooth solutions, meaning that there's a conservation law that says that if I take the time derivative of the energy, then there's a flux function that, of course, is cubic that looks like this, for which the expressing the conservation of energy. Okay, so now if I integrate between finite limits minus L and L, then I've got the time derivative of the energy, right? So here's the integral of the energy, and then evaluating this term, but of course it has, when we integrate, we get limits at x equals L and x equals minus L. So this is an equation that we'll use, but not just yet. Okay, so this is what we're looking for. So I say U plus equals 1, 1 over sigma will be a threshold for U minus. And if we're, let's see, if U minus satisfies the inequality, then we get a picture like this. And if it doesn't, then we just see this linear wave. Okay. Let's see, how am I doing? Oh, okay. Are we trying to stop at 2:45? Is that the plan? Okay, all right. Yeah, should be able to get there. Okay, so close to the threshold. Yeah, so let me talk about this picture a bit more. So we've got a rarefaction wave. We've got some nonsense in here. And then we've got a linear wave. And then separated from the solitary wave. And the solitary wave runs out ahead of the linear wave. The linear wave, remember, is pinned at x equals 0. Okay, so close to the threshold is a single solitary wave with x much less than 0, a linear wave near x equals 0, and the rarefaction wave. And so actually, we effectively have a superposition of those three solutions because there are gaps in between the three pieces. We have to be careful about not double counting U minus. Okay, so here's the rarefaction wave. This is the solitary wave written as a formula, and the linear wave, which we did asymptotics for. Okay, and then the speed c actually has to be determined as part of this calculation. All right, so we assume the linear wave has negligible contribution. These are small amplitude waves. They do have a significant amount of energy, but it's not significant for this calculation, so we'll neglect it. Okay? So a more refined analysis can estimate the contribution. Okay, so we just have two contributions to the energy. We'll take this interval that we integrated over to be larger than the time scale, and then eventually we'll look at, right, and we'll draw conclusions from that, if you like. So the solitary wave is well separated from the rarefaction wave, so we can calculate the energy directly. The rarefaction wave contribution is the energy of the rarefaction wave. Well, we know what the rarefaction wave looks like. Here's the calculation. Remember, U plus is 1, so that's why those 1s appear. And the solitary wave decays exponentially to 0. We have to take off the U minus, remember. And so we get this formula. Here's the U minus. Here's the energy. And we can evaluate that explicitly as well, because we've got a formula for the solitary wave. Excuse me. All right, so we also have this evolution equation written at the top, and we can evaluate what these two limits are at plus L and minus L. Right, we get a 0 contribution from the solitary wave, and then we get we get U minus cubed over 3 from the solitary wave, beyond the solitary wave, and then 1 beyond the rarefaction wave. Okay, and the UXT terms go to 0. So then E of t, integrating this equation, since there's only a constant on the right-hand side, is this linear term in t plus whatever the energy is at 0. But we can calculate the energy at 0 because we know what the initial condition is. Okay, so then we get this formula for the energy at 0. So here it is. We get that formula. Depends on C. And so now we have E of t, which has the rarefaction wave contribution and the solitary wave contribution. Right. So here they are added together. And so we line that up with the equation that we just calculated from the ODE for E of t, and we get this equation. Okay, and it relates C to U minus for a fixed C. Okay. So we get, right, so now I'm going to rescale things. Y is U1 of U minus, X is C over U minus, which is negative. And here's that same equation written out in a somewhat simpler form. And the right-hand side has a unique minimum, which we call R star times C. So here's that. And so we can get the threshold by observing that minimum. There's U minus star. That's the leading ordering C. And so we get an estimate of U minus, the threshold, at 0.295. And C is equal to 0.1. Okay, so it's really just calculated from the energy in two different ways. We have to calculate two quantities. I haven't shown you how we calculate C, but it comes from the threshold for U minus. So here are some conclusions. I've got a couple of minutes, but so there's a paper that appeared fairly recently. I've told you about the Riemann problem for the BBM equation, which is very rich compared with solutions for, say, the KDB equation. And we've addressed some of the issues in resolving those various patterns. I'm going to try and show you a couple of movies. Not sure if this is actually going to work. You think this will work? Okay. BBM movies. Okay. So I'm going to show you, just going to illustrate this threshold. And so what happens, let's see if I can make this larger. Yeah. Okay, so I've got two values of U minus. U plus is 0.5, the two values of U minus, and U minus equals 0.15 or 0.16, and they're in different colors. Okay, and this was when we were trying to discover where this threshold is. So let me play you the movie. There's the big dip, the short time behavior, and the blue curve, which is the larger value of U minus above the threshold, is evolving into a linear wave, and the red curve also has a small linear wave, but it has this solitary wave taking off. Okay. Now, the interesting thing is, another interesting thing, if you like, this was with jump initial condition. I could show you another similar movie, but instead of that, we thought, well, okay, how important is it to have a jump? Maybe we can start with a Gaussian. Okay, so there's a Gaussian. Actually, there are two Gaussians there, right? One's red. There's a little dip here that shows that the Gaussian in red has a bigger dip than the Gaussian in blue. Same limits of plus and minus affinity. And when I play this, so here we have to run it for a long time, but the slow evolution of these waves is kind of amazing. So the blue curve, as previously, evolves to a linear equation, a linear wave, and the red curve is settling down to a single solitary wave. So we've again identified a threshold here, which we have not analyzed. It's but presumably similar calculations work, but we're just dealing with a single solitary wave in this case. All right, with that, I'll stop. Thank you. We'll go back to the slides, I suppose. Of course. Can you? I can't really hear you. Yeah, thank you. That's all right. Yes. Okay, okay, let me answer that. It's really ducking the question, but I'll answer it anyway. So if I go back to the phase diagram, if I go back to the phase diagram, the answer to your question is we chose data in the middle of each sector, and then it's not sensitive at all. So everywhere in here you see a similar pattern. Actually, it's more precisely here, but these are still sectors. If we go precisely on the diagonal, then, I mean, it's not sensitive to where you are on the diagonal, it just scales. So yeah, we haven't, there are interesting issues. In fact, that's how we discovered G, because we thought that F, the picture F, which is a dispersive shock wave after implosion, should evolve somehow to a shock, a lax shock with oscillations. And the way it gets there is by generating all these solitary waves. And the transition, as G approaches H, we don't understand. I mean, we've got some idea, but it's not clear. So there's only really sensitivity in the region G as it approaches H.
Missed it a little bit, but he broke it down into the regions of the different modes. together. And mine was how you decided how many rows.
How many different regions in the phase
All, like,
diagram?
in one solution, one train, said, oh, this is the linear wave, and this is two interacting types.
That was part of the research. I mean, yeah, you have to interpret. So it was pretty clear that this linear wave was a modulated periodic wave. We had no idea about this big black blob at the leading edge initially, and so we speculated that it could be a two-phase wave, but then that didn't explain what was going on ahead of it and so on. So it evolved, yeah. And I should give Thibaut Congy, one of the co-authors, a lot of credit because he picked up on ideas and did the analysis and really helped. It made a big contribution to the paper. As a result, he got, as a reward, I suppose, he got appointed as a lecturer at Northumberland, not just a postdoc. Yeah.
This diagram, how strongly it depends on the size, like this is what size 0.1.
Yes.
You got it as close to 0 as possible.
Yes, it just everything becomes more exaggerated. Yeah.
Okay.
So I mean, for instance, the expansion shock decays algebraically. It goes like 1/t in amplitude, and that the coefficient of 1/t depends on xi.
And the boundaries of different states.
Some of them depend on xi and others don't. Yeah, I haven't written down the formulas, but for instance, between D and E, it's just U minus equals U plus. So this boundary is just the diagonal. But the blue and red and green boundaries, I think they all depend on xi. But so that, you know, they change the angle somewhat. U minus was the first one we found, and there's a separate argument for that threshold between E and F, so where the implosion occurs. Yeah, and it does depend on xi, but it's a rather simple calculation.
That's the end of the seminar. We'll now go to the